Hello everyone, thanks for watching this video. My name is Yang Han, a PhD candidate of University of Texas at Austin. I'm going to present our work, Knowledge-Augmented Contrastive Learning for Abnormality Classification and Localization in Chest X-rays with radiomics using a feedback loop. First, let me introduce the background and motivation. First of all, chest X-rays is one of the most common radiological examinations for detecting cardiothoracic and pulmonary abnormalities. Accurate classification and localization of abnormalities in chest X-rays play an important role in clinical diagnosis and treatment planning. Second, due to the shortage of radiologists, there has been a surging interest in building automated systems of chest X-rays abnormality classification and localization. Third, recently, contrastive learning has emerged as the front runner for self-supervised learning, demonstrated superior ability to handle unlabeled data. We believe it also has the potential to deal with chest X-rays. Following are 5 challenges in our case. First, label and annotated chest X-rays often requires expert radiologists. This process is therefore time-consuming and expensive. Second, unlike natural images, chest X-rays have very subtle and similar image features. The most indicative features are also very localized. Moreover, chest X-rays have both high interclass and intra-class variance. Some diseases of chest X-rays are often weak, can overlap with other diagnoses. Fourth, the class distribution of chest X-rays is also highly imbalanced for available datasets. Last but not least, like I have said before, the most indicative features of chest X-rays are also very localized. Therefore, chest X-rays are sensitive to distortion and not amendable to typical image data augmentations such as random cropping or color jitting. For the method, we use knowledge-augmented contrastive learning. The prior knowledge that we use here refer to radiomics features, commonly used prior knowledge in medical domain. The radiomics features consist of the following 3 categories. First, all the statistic features, shape-based features, grid-level features. All these 3 features are interpretable. Obtaining the radiomics features for our dataset is a chicken and egg problem, which means that radiomics features are highly sensitive and dependent on local regions for which we do not have the local bounding box annotations. Meanwhile, we need to make the image features similar to the radiomics features to learn from the radiomics features to learn localization of abnormalities. This process means the bounding box generation is dependent on radiomics features, which forms a loop cycle. This is the framework overview. During training given set of images, very few images have annotations. Our framework provides 2 views, the image views and the radiomics features. The radiomics features is generated by the BYOP module, which will be explained later. From the image view V, we output the representation Yi and the projection Zi, while image encoder Fi and image projection head Gi, respectively. Similarly, we output the radiomics view YR and radiomics projection ZR, while radiomics encoder FR and radiomics projection head GR respectively. We maximize the agreement between ZI and ZR while contrastive loss. In addition, we minimize the classification errors from representation YI while a focal loss. During testing, only the image encoder is kept and applied to the new X-rays. This is the overview of our BYOP module. For the unannotated images, we leverage Grad-CAM to generate heat maps and apply an ad hoc threshold to generate the bounding boxes. For the annotated images, we directly use the ground truth bounding boxes. Then, with a combination of generated bounding boxes and ground truth bounding boxes, we use the PyRadiomics tool as the radiomics extractor to extract the radiomics features. Note that the generated radiomics features are the combinations of accurate and pseudo-radiomics features for the annotated and unannotated images, respectively. These are the results for disease classification. This table shows the AUC of each class and a mean AUC across the 8 different chest diseases. These are the results for the disease localization. From the figure, we can find that our model can achieve robust and accurate bounding boxes.